All right. Well, if Isabella left, which it looks like she did, I suppose just start talking. Why is nobody talking? Somebody should talk. Somebody say something in chat so that I'm aware my video is functional. Oh, okay. Now it's working. Was it frozen for like a while? Should be connected to my hotspot now. All right, sounds good. So, here's Isabella left, 2 minutes early. So, today, I'm not going to be rambling. Yes, I do have a haircut. You guys should be able to talk to each other. You don't have to talk to only all panelists now. So, I won't really care if you guys can say whatever you want. All right, today I'm going to be going over something really cool with you guys, only for 30 minutes. So it's going to go really quickly. 30 minutes, and I'm going to teach you something called Lagrangian mechanics. And I'm also going to give you a crash course on the calculus of variations, which is like even more advanced than regular calculus. So this is going to be fun. All right. Why is it 2.1428? These are weeks. The unit is weeks. Normally, class on Saturdays, but today is a Sunday. Here's a quote. Because we're going to be learning something hard today. Here's another hard subject, quantum mechanics. But we're not going to be learning quantum mechanics. Unrelated. Still is an inspirational quote though. So, what is calculus? Getting right into it. What is calculus? Okay. We're on the clock. We've got 30 minutes and I'm going to cover so much stuff. So what is calculus? Thing number one, what is a derivative? You guys heard of a derivative before? Well, take a look. Okay. Here is a graph. You can see that. Here is x-axis. Here's the y-axis, except that we're going to be talking about functions, so we're going to call it the f of x-axis. Okay. We're going to have some kind of function, any function. What should I make my function look like? Okay, something like that. Now, let's say I want to take the derivative of this function. I can find the derivative of the function at a certain point. So, what point should I talk about? Let's talk about this point over here. Now, the derivative, you may have heard of this before. I know you guys are all intelligent people. So, derivative is the instantaneous slope at this point. So if I were to draw a line as close as possible to that particular point and try to mimic the function at that point, that would be the derivative. And the slope of that line, that's the derivative. And the important thing about the derivative is it helps us find the minimum value of a function. The minimum value. What's that mean? Well, what is the minimum value of this function that we can see? Well, there's two minimums. One of them is over here. That's a minimal point. Here's another point, minimal point right over here. If you notice them, what is the derivative at this point? We're going to be trying to draw the line absolutely as close as possible to that point. This. It looks horizontal. And if the line is horizontal, the tangent line, that's what it's called. The tangent line is horizontal. Slope. Slope is 0. So, the derivative is 0. We don't necessarily have a minimum. We don't even necessarily have a global minimum, but we do have a local extrema. See, like over here, this point's not the minimum, but around it, like from here to here, it is the minimum. That's why it's called a local minimum. Over here, this point's a maximum, but it's also got a zero derivative. But in general, if it is a minimum, then it must have derivative 0. Must have a derivative of 0. So, everybody with me so far? It's okay if you're lost already. Well, might be a little difficult for you to follow if you're lost already. But 2 important points so far. 2 important points. What is the derivative? At any particular point, I can calculate the derivative of the function at that point by looking at a certain point and drawing the line, the tangent line at that point. And once you've got that tangent line drawn, you figure out what the slope of that line is, and that will be your derivative at that point. Second important point, the local minima and maxima, the extrema, they're all going to have a 0 derivative. There are some caveats, which I'm not going to go over here. If you take calculus, you'll learn about them. But physics, we're not worried about the mathematics. This is all you have to understand. Oh, and what is the notation? The notation for this. If you think about it, I can find a derivative of any particular point, right? I can find a derivative at this point, 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 all of the points. And if I take all its derivatives and put them together, I can make a new function, right? I can make a second function. If I start with an original function, f of x, and then let's say I find a derivative of this at a certain point, like at 5, then I'm finding the derivative at 5. But I can also find a derivative at any point, and that function is called d over dx of f. d over dx of f. Lowercase f. What does this mean? Well, you have to think about what slope means, because we're looking at the instantaneous slope at each of these particular tangent lines, right? So the slope, what's the slope? The slope is going to be, probably we're taught this in school, delta y over delta x, except in this case, we're not looking at y, right? The y, f of x. So all we're doing is delta f over delta x. The thing is, mathematicians don't like to use this triangle. It takes too long to write. df over dx. This is not by any means vigorous, but helps explain this. If you want to, you can think of this as a delta symbol, delta f over delta x. This means change in f over change in x is the slope. That's got to be the derivative. And keep in mind, this is a function. So for example, you can find 5, right? Just like you can find f of 2, find df over dx. Okay? That is the derivative in a nutshell. We're only going to be looking at the minimization part of the derivative. So actually, probably going to go beyond that. That's okay. Minimization. Almost all of basic mechanics, if you understand derivatives, you can do all of it. For example, what is velocity? Velocity is change in x over change in time. So if I draw x of t, right, and here's a trajectory, if I want to find a velocity of time, really just derivative of x with respect to t time. What time does class end? It ends at 6. Oh no, it does not end at 7. It's special class. Oh yeah, EST. Sorry about that. 30 minutes. It's only 30 minutes. No matter what time zone you're in, might be a different time, but 30 minutes. So that's the velocity. If you want to look at acceleration, this is equal to the derivative of velocity with respect to time. And another way to write this is the second derivative of x with respect to t. So immediately we have derived velocity acceleration. From here, you multiply this by mass. You get momentum, you multiply this by mass. F equals ma, you can get the force, right? And then from here, you can just get bigger and bigger. Work your way up. Work your way up. Got a stack of fresh papers. I don't need to reuse them. Who cares about trees? Okay. No, everybody cares about trees. Global warming is a real thing. Integrals in a nutshell. What is an integral? Let's check it. So, basic idea of an integral is if I've got a bunch of really small things and I want to add them all together, that's what an integral is. So for example, if I want to, I've got this little hill over here, okay? This is a hill, little hill. That's a hill. Hill is made of sand. So I'm at the beach, all right? I'm at the beach. This is a hill. It's made of a bunch of little particles of sand. And I ask you, what is the total mass of the sand? What is the total mass? Total mass, there's two ways to do it. You can weigh the whole thing. If you just weigh the whole thing, that's going to give you, it's going to give you a weight. But you can convert that to, as long as you're on Earth, you can convert that to kilograms, mass. All right, so that would be M, big M, the total mass. But this is also equal to the integral of little tiny pieces of mass. And if you're looking at a little tiny piece of mass, remember how we said here, df over dx? This little dx over here means a very small change in x over a very small change in f, right? D means very small. So, yeah, these mean the exact same thing. If you take the integral of anything, like for example, what else? Let's say we're looking at the volume of this, okay? You can measure the entire volume. Oh, why am I using this weird Roman symbol instead of this? It's because if I use this, it looks like velocity. So instead I use this. Looks like a smiley face with a ton sticking out. Okay, bad. Velocity. Volume. Volume is equal to the sum of all the tiny little volumes inside of there. All right. There's two different ways we can take a look at the entire volume of the amount of sand. Just calculate that, or we could look at the volume of every single individual piece of sand, grain of sand. The grains, right? Sand is measured in grains. Every single little grain of sand. You can add them up. That's what an integral is. Wow, 10 minutes. 10 minutes. That's all you're getting on calculus, and we're moving on. All right. All the people in the chat, all the intelligent people in the chat, what is the shortest curve you can draw between A and B that connects them? Ooh, somebody got it. A line. Line. Wow. You guys were smarter than me. This was my first attempt. Probably not that. I don't know. I really don't know. We're going to figure it out. We're going to figure it out. A lot of you guys say a line. Not sure how you guys are so sure of that. A line is a curve. A line is a curve. Before that, we're going to do some calculus of variations, which you guys are never going to learn in school because it's probably way too advanced. They might teach it to you in college. I'm going to teach it to you right now. What is the calculus of variations? So, for here, remember how we said we could minimize function? Use f of x. F of x. Here's x, right? And we're trying to minimize the value of f of x with respect to x. We can change x. We can change where x is. We're trying to minimize the value of f of x. But here, what our question asked us was, we got 2 points. Okay, we got 2 points. We've got 1 point, xo. Okay, we're gonna call this xo. We're going to call this point. I'll put it up here. x1, and we've got, I don't know, I'll call this y. Call this y1, and we are trying to find any curve that connects these 2 points. Right? Any curve that connects these 2 points, and we're trying to minimize. We're trying to minimize the length of that curve. So really, could be any curve. Right? This is our function. This is our function, f of x. We're trying to prove that f of x is a line. Right? We're trying to prove that it's a linear function. But we don't know that. We don't know that. We aren't very intelligent. Somehow we know calculus of variations, but we don't know basic geometry. f of x. This could be any function. So what are we trying to minimize? We're trying to minimize the length of this function. And there's a lot of possible functions. In fact, there's an infinite amount of possible functions. There's an infinite amount of possible points, like I can pick any one of these points, but the number of possible functions is much, much bigger than the amount of possible points. But we're only looking at continuous functions. We're only looking at certain calculus term functions that are nicely behaved because we're physicists. So what can we do with them? What can we do with them? We're trying to minimize the length with respect to the function instead of the variable. We're going to try to find something such that small changes to the function only make the length bigger. So let's say this was the solution. This is not the solution, in case you didn't notice. But let's say this was the solution. Then a very small changes in this function. Let's say we made a change, and now the function looks something like this. Okay, here's a new function. Do you see the dotted line right here? We took the function, and here this new function, call that f of x plus some very small function of x. And here I did not make up that symbol. That symbol, that's a lowercase delta, I'm pretty sure. And instead of using delta f x, because that means a large change, or df of x, so that means an infinitesimal change, but this is not a proper differential, right? Because it's an entire function. This is what we got. This is what we got. So, yeah, by the way, you're not allowed to, this is not correct, okay? This is, whenever you have like a df or like a delta f, think about that as one symbol, right? Think about that as like one math word. It's kind of like how you're not allowed to say sine of x is equal to s times I times n of x, because sine is one word, right? Okay, same idea, okay? Delta f, think about that as one thing. One thing. Pretty sure vegans don't eat trees. Somebody just asked me that. Anyhow, yep, calculus variations, that's that. Euler-Lagrange equation. This is picking up exponentially, okay? So if we're trying to minimize something along the lines of this, ooh, scary, what does this mean? What this means is we're trying to minimize, we've got ourselves a function, any particular function, and we've got a different function. We've got a function of a function, y and y prime over here. Y is a function, and we're taking a function of a function. For example, in this case, our y is any particular curve that you can draw, and f is the length of that curve. Right? So we're taking a function of a function, and we're trying to minimize the integral of this with respect to the entire function, because that will minimize the length of our curve in this situation. So let's take a look. If we're trying to minimize this, how can we do that? We must have this. Why? I'll show it to you. I'll show it to you real quick. Here's a derivation, and will be very interesting. Let's check it. We start with y. We start with y. Y of x. And we're going to add something. I've got all my physics up here. I've been looking up. At it. Okay, so we got y of x. What are we going to do with it? We're going to take it and we're going to add very small y to it. What are some properties of this? Well, something about the calculus variations is that the end points are always fixed. Xo, yo, x1, y1, fixed, right? For example, we always have the starting condition and the ending condition. So if we're going to try to add a function to this, it's got to preserve the beginning and ending. So of x0 must be equal to 0, must not change. And this must be equal to 0. Because think about it. What we did was we took this function over here and we added a second function. And we want to make sure that these 2 points don't move. those have to end up being 0. Right? So now what you do is we try to take, this is going to be very interesting, okay? What we're going to try to do, take the integral is, this is not proper notation, this is a heuristic derivation. We're going to take this derivative with respect to y. How about that? With that. This is going to be equal to what? It's going to be equal to what? This has got to be equal to 0. Why does it have to be 0? Remember how we said before that if you change x slightly, if the slope is 0, that means if you change x slightly, y barely moves. That's how you know that you've got a minimum. So you do this. Now what? Now what? Looking back up. I'm looking back up. Use the change rule. What is the change rule? Okay, let's take a look. What we started with was f of y comma y prime. F of y and derivative of y. If we want to take the derivative of this, we're trying to take derivative with respect to change in y of this. We can swap them because we're physicists and it doesn't matter. From x0 to x1. And because of the change rule, what can we do? We can do x0 to x1 of, got to take the derivative of each part of this. Got to do d over dy of straight up df dy of delta y. Plus, a little difficult. Why does this work? Ask somebody who actually knows calculus. Do this, make some cancellations. You use it's called integration by parts. You guys probably don't know integration by parts. The way you do that is you can take this little y prime over here, move the prime to the other thing. What you end up with is something along the lines of, all that stuff cancels out. What you end up with is something like the integral from x0, x1 of, that's the integral partial of f, partial of y, minus d over dx of partial of y over partial of y prime. What does this say? What does this say? Times dx. We're trying to set this equal to 0. Easy way to make something equal to 0 is make the part on the inside equal to 0, because take the integral of a bunch of zeros. Remember, we're just adding. It's got to be equal to 0, right? This is saying if you add up a bunch of little zeros, if you add them all together, you're going to still end up with a 0. So the easiest way, take this part over here, turn it into a 0. What's that mean? Partial of f over partial of y minus d over dx times partial of f with respect partial of y prime must be equal to 0. And let's take a look to see if I did it correctly. I did. Okay, that's sweet. Anybody follow that? Probably not. Great. That's the Euler-Lagrange equation, and we're going to apply it. Solving the plane geodesic problem. What is the plane geodesic problem? What is a plane? A plane, like a two-dimensional Cartesian plane, that just means two-dimensional flat surface. That's all a plane is. Geodesic. What is a geodesic? A geodesic in any particular surface. In any particular surface, a geodesic is the shortest path between 2 points. So for example, this is not necessarily always a line. So for example, if you had something like a sphere, right? Pretend we had a sphere. This is what a sphere looks like, and I'm trying to find the shortest path from A to B on the sphere. Have you ever been on a plane ride and you were watching the maps? Like if you're on an international flight and it's like a really long flight, lasts overnight, you might have a little screen in front of you that shows you the path that your plane's taking. It's pretty cool. It's not going to be a straight line. It's going to be curved. Why is it going to be curved? Because the surface of the sphere is curved. So that's what a geodesic is. What is a plane geodesic? A plane geodesic is shortest possible curve between 2 points on a plane. And that's exactly what we're trying to find. trying to find the shortest possible path between any 2 points on a plane. Then we'll solve the question. So how do we do that? The details will be worked out on paper. Why didn't I put them on a slide? I don't want to do this right now. All right, let's do this. Basic idea. X, Y. Got ourselves a curve. And in fact, we're only going to look at a very small portion of the curve. So here's our curve. We're going to look at this small portion over here. Looks something like this. It's going to have a small distance, dx. It's going to have a small distance, dy. Anybody know the Pythagorean theorem and can tell me the length of this? Anybody? Just pretend these are variables. Pretend this is a and this is b. Then what's the length of the hypotenuse? Anybody tell me? Come on. Nobody knows Pythagorean theorem? Somebody got it. Somebody got it. Square root dx squared plus dy squared. And now, what can we do? We can take this thing, multiply by dx divided by dx. If I give you an apple and I multiply by 2 and I divide by 2, I still have an apple, right? So we got 1 plus dy over dx squared times dx. Is that correct? I think that's pretty much correct. And now we're trying to find the total length of this. Total length. The length is just the integral, bunch of small lengths, right? dl. Very small lengths. And the very small length, this is dl. So what is dl? L is in fact equal to integral from xo to x1 of 1 plus dy over dx squared dx. This is what we're trying to minimize. We're trying to minimize dl. We're trying to minimize L. And how do we do that? Here's the equation that we just came up with. Do you guys remember? Of course. You might not. That's okay. Might not. It's this guy over here. I've got it up for reference. And got to solve it. Simple enough. We have our integral. Oh, yeah. This is what we've just worked out. Y prime. What is y prime? We had a dy over dx. Dy over dx, remember how I told you guys earlier that that's exactly what the derivative of a function is? Y prime is just another way of saying that. Great. Okay. Go ahead and try to minimize this. How do we minimize this? Well, according to Euler-Lagrange equation that we derived from earlier, we know that partial of L over partial of x. Make sure I'm getting that correctly. Yes. Almost. Almost. Minus d over dx times partial of L over partial of y prime must be equal to 0. Anybody knows their calculus? This is equal to xo to x1 square root of 1 plus y prime squared dx. And think about this little expression over here, 1 plus y prime squared dx. There's no y there. We've got a y prime, but y prime and y completely different. So this is 0. Bye-bye. We've got d over dx of partial of L over partial of y prime is equal to 0. What is the partial derivative of L with respect to y prime of this? Well, if you happen to know some calculus, you might use the change rule. How do you use the change rule on this thing? Good question. That's a good question. And it's a good thing that I got it written over here. You end up with something along the lines of, if I've already got it on a slide, I don't have to work it out on paper. D over dx of y prime over the square root of 1 plus y prime squared is equal to 0. And the derivative of something is 0. Remember how we said d over dx? That's just a slope, right? If the slope of something is 0, can you guys follow? If the slope of something is 0, there's got to be a straight line. If something's a straight line, then, well, it doesn't change. So this little part on the inside over here, y prime over 1 plus y prime squared, square root of 1 plus y prime squared, doesn't change. So dy prime dx is 0, which means slope is constant. We're done. This took longer than I thought, and I was hyper accelerating it. That's okay. I'm sure you guys the Lagrangian. What's the Lagrangian? All physical phenomena and all physics. Remember how I told you guys that F equals ma? That was the solution to all physics problems ever. Well, turns out to not be very useful. Well, it is useful, but the hard part ends up being figuring out what the force itself is. And here's a way to do that with energy. You use energy in order to figure everything out. What is T? T is kinetic energy. Why did it not use K? I don't know. It's probably already a unit for Kelvin, so that would be confusing. V is potential energy. And L is the Lagrangian. At least they did something like that. It's not length, it's the Lagrangian. It's equal to the total kinetic energy minus the total potential energy. And the integral of this with respect to time is minimized. Why is it minimized? Well, all you have to do is take a look at the Euler-Lagrange equation, and here it is in the plane. Here it is in the plane. Here's the kinetic energy, 1/2 m times x dot squared. What is the x dot? X dot is yet another way. It's x prime, x dot, same thing. They changed the location of the little comma and they moved it to the point. And it's also the same as dx dt. These are all the same as velocity. Change in x with respect to time is velocity. So 1/2 mv squared, you guys might recognize that as kinetic energy. That's exactly what we want. V of x, that is potential energy. So we're good here. That's the Lagrangian. And all we have to do is plug it right into the Euler-Lagrange equation that we derived from earlier. We did not derive it. Just kind of threw it at your face. Okay, if you do that, here's what you get. And why does this make sense? Why does this make sense? The partial of the Lagrangian with respect to x is what? This part has the x dot, completely unrelated to x. This part is the potential energy of x. And the derivative of the potential energy with respect to x is the negative force. So the negative derivative of the potential energy with respect to x is the force. And over here, what's this? Derivative of the Lagrangian with respect to x dot. There's no x dot on this side. There is an x dot on this side if you know calculus. The derivative of 1/2 mx squared, mx dot squared, is equal to mx dot. Mx dot, that's mass times velocity. Mass times velocity. Okay, so that's momentum. And take the partial derivative of momentum with respect to time, get mass times acceleration. So this is just our old friend F equals ma. It's expressed in Lagrangian mechanics. Shoot, I was going to get to some other stuff. Looks like I'm all out of time though. We were going to get to all this fun stuff. And angular. And if you guys thought that was hard, the last 30 minutes, here are my notes. They're on the wall behind me right now. It's for spherical coordinates, not too complicated. It gets a little more complicated if you add in everything else from the standard model. And then if you expand it, you get this. It's a real equation. Somebody wrote this down. Somebody wrote this down. Okay? Well. All right. That's it. Have fun, guys.